In this video, I want to talk about the halting problem. The halting problem is the problem of determining whether a function, for example, a Python function, contains an infinite loop or not. The British mathematician and computer scientist Alan Turing discovered more than 50 years ago that it's actually impossible to solve the halting problem in general using an algorithm. You cannot write software that takes in a Python function and determines whether it contains an infinite loop or not. In fact, you cannot build a machine that can do that at all. Alan Turing proved that, and I'll show to you how in this video. So first of all, let's get clear about the problem. So the problem is, take a function that's like that, or like that, or like that, and determine whether it contains an infinite loop or not. Pretty clear what's going on here. Clearly f does contain an infinite loop because it says, while true, pass, which means just keep looping forever. What about g? Well, g also has an infinite loop in it. Why? Well, because the only way that this loop stops is if n is both prime and even. But since n starts at 3 and only increases, that means that we will never find an n that satisfies this condition, because of course the only even number that's also prime is 2. This is not a very interesting insight, but you have to have it in order to figure this one out. What about this one? Well, this is a function that we saw a few weeks ago. What this function does is look for a counterexample for Fermat's last theorem. And of course, we know from Fermat's last theorem that if p is 3 or greater, then there is no solution. There are no I and j and k such that I to the p plus j to the p is equal to k to the p. So if p is greater than 2, then we know that this is an infinite loop. However, in order to actually figure that out, mathematicians had to spend upwards of 200 years thinking about it and writing down proofs and theories that led up to the proofs. So you can see how the halting problem is extremely difficult. So in a way, it's not super surprising that you cannot do it algorithmically. What is surprising is that you can prove that you cannot do it algorithmically. So let's proceed with the proof.